Hello and welcome to another episode of Deep Dive into Applied Science. And today we have a special episode because for the first time we have a different setup and we actually have two guests with a very special PhD. And those two guests can introduce themselves.
Hi, my name is Isabelle Barth and I'm doing my PhD since 2023 at the Environmental Campus in Birkenfeld together with...
Yeah, my name is Lauri Hoffmann. I do my PhD studies too at the Environmental Campus in Mechanical Engineering.
Perfect. Thanks for introducing yourself. So, you're both from UCB, but before we dive deeper into anything else, please describe your PhD in one sentence, if even possible. That's probably a hard challenge, but yeah.
I optimize bioreactor mixing processes by customizing the bioreactor internals for the organism we want to cultivate. In our case, it's a fungi.
Help me out here. What exactly is a fungus? Just for the people that don't know what a fungus is, including me.
So maybe I can dive in because my topic is the cultivation of the filamentous fungi. And next to the plants and the animals, we have also the third part in the biology where the fungus is sitting there. So it's like a microorganism. In our case, the most people know the mold or also the mushrooms that we know from the food. And in our case, we cultivate the filamentous fungi in a bioreactor, and I try to optimize the bioprocess to get higher yields in the production of pharmaceutical interesting substances.
So for an outsider like me, this sounds both very complicated. So why did you choose this topic exactly? That's a question for both of you. What is it that interests you? If you want to, you can start.
I chose this topic due to its interdisciplinary character. Because in school times I was very interested and fascinated by biology, but I decided then to study mechanical engineering because I'm also very interested in understanding technical processes and machines. And now I can bring both topics together again, and that's my motivation.
Yeah, the interdisciplinary aspect is also very interesting for me. But another thing that drove me into this topic was that in the beginning of my bachelor degree or in the end of my bachelor degree, I already was able to do my bachelor thesis in the same lab. And I could dive deeper into the topic with the filamentous fungi in some projects and also my master thesis. So I was already really inside the topic and had a big knowledge about everything. I knew the experimental setup and also the facility, so it was easy to dive in, and now I can focus more on the deeper parts.
Sounds fitting. So take me with you. How does your everyday research look like, and also the interaction between you two? How can I imagine your PhD?
Well, our research is based on the comparison between the experimental or real laboratory work of Isabelle and my more virtual digital simulative and design work of the mechanical engineering part. And you should think about we need this experimental part as a control unit for the simulative part, and we need the simulation for the optimization of our microorganism cultivation process. And so we have some cyclical iterative process between us both, and we choose information from each other, and we test this new internals for the bioreactor afterwards, also in reality. So there's always an interdisciplinary character in this project.
And correct me if I'm wrong, but the end goal of your project is that the fungi, that the fungus grows faster and bigger?
No, not exactly. So the fungus can grow in two different morphologies. The morphologies is like the shape of them. And one of those morphologies is the pellet form. It looks like small little balls or really small spheres. And if we have this morphology, then the fungus produces a pharmaceutical interesting substance. We found this out in preliminary studies. And so we try to get more of those pellets. And the size is not really controlled yet, or we don't try to influence the size, but we try to see some differences if we change the morphology. The second shape that they can take is the filamentous. Free hyphae is the name of it. And so it's like some filaments that grow all together, and it looks a little bit like a nest or something. So it's very viscous, not so fluid substance, and everything is mixed up in the bioreactor. And we just try to get them as the small spheres.
So you are researching reactor internals that make the mushrooms grow, well, let's say, grow more carefully and also stir them more carefully in their growing process. How exactly can I imagine this?
Imagine you would like to mix a cocktail. So you take your ingredients, like some berries or some crushed ice, and give this into your glass.
I actually have no clue about cocktails.
Yeah.
That's another topic. Yeah.
Yeah. But then you have your glass and you have different ways to mix your cocktail. You want a mixed cocktail, not a not mixed cocktail. Yeah. And so you have different ways. You can steer it with a simple stick very slowly, but then it takes a lot of time until it's mixed. Or you take a professional mixer and mix it very fast, but in the end, then you have not a cocktail anymore, then you have some kind of smoothie. So, and maybe Isabelle can bring this back to scientific context.
Yeah, so in our cultivation context, we can imagine that the berries are our fungi. So we have them in the fluid, and if we mix them too hard, they get destroyed. We will get a smoothie-like consistence and those free hyphae. But we want the pellet form, so the small spheres, to not be destroyed. So we have to find a way to mix them well enough that they are really mixed in the whole bioreactor, but also not too much to not destroy them. And this mixing behavior and the simulation of the flow field can help us to analyze these forces. Those are called mechanical stress or shear stress.
Shear stress.
Yes.
Yeah. Like you shear.
Now I get it. Okay, thanks.
Yeah. And yes, we can influence those forces by changing the geometry or the process parameters.
So you already mentioned various times the reactors. How exactly are they built, and also how big are they?
So first of all, we have a bioreactor that we bought. It's a glass bioreactor with a double wall. There's some hot water outside to make the temperature control. And we cultivate in a 2-liter bioreactor. So we have 2 liter of our fermentation medium inside it. And we can also go to a scale to 10 liters. And then the next step is that we have some bioreactor internals like the sensors or also some stirrers, and those geometries could be changed by Lauri, who can explain how he can make some new geometries.
Yeah, I develop a new geometry in a virtual room. It's some kind of virtual 3D model, and afterwards it's the aim to print this model in a 3D printer because it is the fastest way to produce a prototype. Yeah, and we have there also new possibilities for geometries. We can print with 3D printer. So I take this model and I divide this model with a special software in the so-called slices. So in general, the 3D printing process, it's a layer by layer process. So we need to cut this 3D model before we print into those slices, and then we bring this data to the printer. For the printer itself, we have different possibilities. We have for example, the so-called wet photopolymerization. In this printer, we have a small basin at the bottom of the printer, and this basin is filled with so-called photopolymer resin. So this polymer is hardened by light. And underneath this basin, it has a transparent bottom. We have a LED matrix. This LED matrix makes light along the structure of this part. And afterwards, the building platform where our part is sitting on is driving upwards. And then the part grows layer by layer out of this resin. Yeah, that's one possible.
But that's a robust material.
Yeah.
So the fungus cannot harm it in any way.
That's a polymer in this case, but we can also print metals like stainless steel, and which is common in bioprocess engineering. Yeah.
And how exactly do you control the growth of the fungi? Do you play with temperature or something else?
Yes, so what we did until yet was to change the medium composition. So we gave some additives into the medium, or we tried to have some different concentrations of some ions to change the growth. And also we can change the stirrer speed. If we stir faster, they have more forces. If we stir slower, it could be that the forces are too low and all the pellets will sink down. So we have a lot of parameters where we can play around with it. And after all those changes, or also if we change the geometry of a stirrer or something, we will look at the production of our secondary metabolite. So we will calculate the yield and find out if they produce more or less of the substances.
So if you don't get the expected growth, you just change one of the components and hope that it works out. Okay.
Yes, exactly.
Your project is structured as a so-called Promotionskolleg, which is a very German word. So how does this Promotionskolleg look like?
We have different or several project partners in our project. We have, on the one hand, project partners at the Johannes Gutenberg University in Mainz and the TH Bingen. And on the other hand, we have our parts at the Environmental Campus in Birkenfeld. At the Johannes Gutenberg University and TH Bingen, they work at the more analytical part by analyzing the secondary metabolites of the fungi. And we have the more bioprocess engineering part by investigating the steering process and the cultivation process of the fungi. Yeah, and we produce the fungi. And the secondary metabolites and send them to the other partners in the project so they can make their analysis. Yeah.
And when exactly did you two start your whole PhD?
I started in summer 2023 and she started in the beginning of 2023.
And if you look back at your work so far, what were the biggest challenges so far?
One big challenge in the cultivation of filamentous fungi is that there are a lot of variations. So if I try to do the same experiment a few times, the result is not really clear. So if I have a mathematical equation and I do some math and then I have a result, it doesn't change. But if I put the same fungus with the same media and I don't change anything, we have a higher variation between the results. So especially the reproducibility of the filamentous fungi cultivations is a little bit challenging. But we have always surprises in our daily work, so it makes it also interesting.
Yeah.
Sounds like a good thing.
Yeah.
What about you?
And in my simulation world, it's the most difficult challenge is to represent the reality in the best way. And in the same way, make the simulation not too complicated. It's always, I have to look that those both points are very equal. Yeah, you have a lot of settings and a lot of buttons, and in the beginning, you don't know which button to press. And afterwards, then you go deeper into the theoretical background, and then that's a step-by-step work, but it's also always a challenge.
Maybe some people ask themselves what or for who exactly you are doing this. So which I don't know, which industries, which companies can profit from this, let's say from the growth of the fungi?
Yeah, we have some bioprocesses already in the bigger industry scale. So for example, the antibiotics production or also citric acid production is already performed with some filamentous fungi cultivations. And one point is that the deeper understanding of the morphology and the processes in the filamentous fungus would help to get some more stable processes, and it could help to get more consistent results. As I already said, we have a high variability, and the deeper the understanding of it, maybe we can control it to get higher reproducibility. The production of secondary metabolites could be one part that could be optimized. And also we are investigating a special secondary metabolite who could be interesting later for the pharmaceutical use.
So if I'm correct, the pharmaceutical industry profits from it, but also other people can basically use your work and use your results.
Yes, exactly.
And if people are interested in you as a person and also your work, how can they contact you? How can they reach out to you?
They can contact us via email. I think it can be put in the info box or something, or via LinkedIn. And if you have some questions about the cultivation of filamentous fungus, you can reach out to me, or if you have interest in the customized bioreactor internal parts or something, you can reach out to Lauri.
Also, both of your PhD projects have dedicated sites on the website of Trier University of Applied Sciences, and if people are interested, they can take a look at any time. So thank you very much for presenting the growth, the cultivation of the fungi. I accidentally called them mushrooms before we started this session. So that's not a scientific word for it. But thanks for coming on. It was very interesting. And also thank you very much for listening, maybe for watching. And we will see and hear each other in the next episode of Deep Dive.